Alright, so the first question is just taking the matrix from tutorial 3, and it's just asking us to find the kernel of t and the range of t respectively. So provided this thing down here, right, so given some transformation t that goes from v to w, we have that the kernel of t is a subspace of v, which is the first one, and the range of t is a subspace of w, which is the second one. So in this case, we have that the kernel of t is a subspace of R5, and so we can deal with the definition of what a kernel is, right? So if we have some kernel of t, that just means we're setting a transformation equal to 0, which in this case, since t goes to ax, that means we have ax equal to 0, which from definition of a null space is just the null space of A. And we go back to what is a null space? Well, a null space of some matrix is just setting the matrix equal to 0. So we have the null space of A goes to A is equal to 0. Given we have A up here, we just get this matrix equal to 0. And from tutorial 3, we just try to row reduce if we can to get REF to find our null space. Simplifies it. So we end up with, we can row reduce this one over here to get this. So we have our x1, x2, x3, x4, x5. We cannot row reduce anymore, so this is our REF. So then we see that x3, x4, and x5 are all free, right, as it has 0 equals 0, and all the other rows are taken up already. So that means we can let x3, x4, x5 equal to some parameter. We can define them to be t, kp, element of some field, since it's not defined up here once again. So then we get the null space of A, which is going to be the kernel of t, is equal to the set of, since we have 5 columns, we have 5 different possible inputs. So we're going to store that as a column over here for our column input. So you get x1, x2, x3, x4, x5 is equal to, and we move everything over here to the B slot. So after we do that, we're going to keep them with respect to their variables, right? x3 is t, x4 is k, x5 is p. Then we're going to store them like this. Then we're going to split them up to get t, k, p. And then when we rewrite them as like a span, right, we're going to take the first vector, the second one, the third one. We're going to split them up like this as the columns, as the span can be any scalar multiple, as we've defined over here. So this is the solution. Right. Then the range of t is going to be a subspace of R3. If we look up here, we see that R3 is with respect to the columns, right? We have 1, 0, 0, 5, 1, 0. All the columns are just of R3. So we notice that that is with respect to, under this transformation, the column space of A. And so we can just write our span to be all the columns of A here, right? But I didn't leave a little note because I saw some people get confused with this. If we wanted to write a basis for the column space of A, we would only take the pivots, but in this case, it's not asking for a basis of the column space. It's just asking for what is the column space, so we just take all the column spaces of the original matrix. And in the case where you cannot use the RREF matrix, because that does not preserve the column space, right? That can change it. So in the case where it asks for the column space of A, you cannot use any row reduced ones, you just use the original. Yeah, and I wrote it here. So if you want a basis for the column space of A, you take the pivot columns, because in this case, non-pivots will imply that it's a free variable, which will imply that it's linearly dependent, which will imply that it's not a basis, right? So you're just going to use that little fact. All right, number 2 is just solving differential equations. So for the first one, A, we can just let the differential order represented by like dn, right? So if we have y triple prime, that'll be d to the 3, because it's of a third order. Y double prime is d2, y prime is d1, and y is not of any differential order, it's just 0, so we can treat that as a constant with respect to how we've defined what dn represents. So in the case we have y double prime minus 3y prime plus 2y equals 0, we just sub in the pieces up here that we got, right? So we have y double prime goes to d2, y prime goes to d, and y just goes to some constant I that we've defined. And we write that all with respect to the variable y. We have not gotten rid of it. We're just representing this in a different form that's going to make it easier to deal with. Right, so then the next thing we're going to do to make this even easier is we're then going to factor this out. You could use the quadratic equation to solve this, but factoring is just much simpler to recognize that we have a 3 and a 2, so that's going to go to -2 and -1. -2 plus -1 equals -3, and -2 times -1 goes to 1, goes to 2. Right, so that's a really quick way you can factor that. After we factor, we're going to split all these up into different pieces to find basically what the sum of them are going to be for solutions, the form that they're going to be in. Right, so we just take the first one here first, and I like to represent that as y1. Set that equal to 0. Then we're going to sub our y's back in. Right, so if we have d minus 2i, well, that's just y prime minus 2y1 equals 0. Since we're dealing with y prime, we're saying that's with respect to the derivative, so we can actually rewrite that to be dy over dt. I think that's the Newton's thing. Some people were like, does the variable oh god, my throat. Does the variable on the bottom matter? It doesn't really matter, right? Like you can do like dx, dA, dB. I just do dt because that's commonly how we represent differential equation solutions. Right, so it doesn't really matter just so long as everything else is correct. But yeah, we get move this over here. We get dy over dt equals 2y1. Then we can move the y back over here to divide that, so we get dy1 over y1 equals 2 dt. Now what we're going to do is we're going to take the integral of both sides because we want to get rid of the y prime or the derivative, right? We just want to get y by itself. When we do that, we get the integral of 1 over y dy. And some people were confused about what that was. If you haven't taken calculus, that's understandable. You can kind of imagine just the integral to be the opposite of the derivative. So if we have, say, like, what is the derivative of some function to get to 1 over y, and we can recognize that that's going to be ln y, right? So the derivative of ln y is 1 over y, so the integral of that's going to be ln y. But when we do the integral, we're going to have some constant left over, right? Because when we differentiate, we get rid of the constant. So after taking the integral, we're going to add some constant because we're not sure what the shift is necessarily. That's not factored into the velocity function with respect to the position. Yeah, so we take that, right? That's ln y. And then the integral of 2 dt is just 2 times, well, the variable t. So we get ln y equals 2t plus some constant, as mentioned earlier, because we're not sure what the shift is. Then we go up here and we try to look at the properties of logs, right? Because we have ln, which is a natural log. We notice that we can get rid of the log by, if we have some log base a equals c, that just goes to a equals the base of c, base to the c. So ln y equals 2 plus some constant 2t plus c1. That's just going to go to y equals e to the 2t plus c1. And then we take exponential properties. I'm still sick, damn it. And we take exponential properties, say that if we're adding an exponent on the top, that's just the same as multiplying by the same base. Right, so e to the 2t plus c1 just goes to e to the 2t times e to the c1. And as I mentioned earlier, we're not sure exactly what the scalar constant is here. So we can just define e to the c1, it's just going to go to c1. Right, that's about it. And I did a little general form here. So if we have AD minus BI is a factor with respect to y, that's just going to end up being y equals B plus C1, well, BT plus C1 over A. It's important to note that you have to take consideration of the sign here. Right, if it's minus B, then it's going to end up being positive B. If it's positive B, then it's going to end up being negative B. Right, so it's just negative b on top. A is going to be the exact same sign. So that's how you're going to deal with that. So we're going to use this general form over here to try to figure out what our other factor is, d minus I, y2, because this is our second solution. Second solution piece, I should say. So that's going to get y2 equals c2, and we see that we have a negative 1, so that's e to the negative 1 times negative 1. With t, so that's just e to the t. And then we represent the solutions to be of the form of our kernel, of our transformation over here, or of our function. So this is y equals y1 plus y2. So we take our, where's our y1? There's our y1, there's our y2. Right, so then we're just going to write c1 e to the 2t plus c2 to the, well, c2 e to the t. That's about it for that. But yeah, you can just skip from this step if you wanted to all the way down to here. That's completely fine. You do not need to show all of this unless it's asked. This is just where it comes from. But yeah, then there's b. So how do we approach b? Well, we're seeing that we have our differential equation equal to some p2 polynomial. So that gives us a hint of what to do. So since this is equal to some p2 polynomial, we're going to let our y naught, which is our initial function, be equal to a plus bt plus ct squared. And since we have y double prime and y prime in the equation, we want to find those pieces so we can sub them back in later. Right, so that's y prime for our initial. You're going to set some arbitrary p2 function, a plus bt plus ct squared. That gives us y prime naught equal to b plus 2ct, and then y double prime equals 2c. Right, so after we get these three pieces, we're just going to sub them back into here just so we can actually finish solving. So y double prime just goes to 2c, so we're going to put 2c there. Y prime goes here, so we're just going to put that there. And our y is just this, so I'm going to put that there. Then after doing that, we're going to approach this like we do with some problems in tutorial 3. Right, so we're going to group according to their coefficients and their degrees. So here we have a constant, a constant, a constant, and we have a constant solution. So we're just going to group them all into constants here, as I represented here. Blue goes to blue, green goes to green, and yellow goes to yellow. So after you group them all together, you're going to get three different equations over here since it's a P2 and everything is present. So then we can store this as a matrix to solve, or you can just use substitution. That's completely fine as well. But yeah, since we have three different pieces, A, B, C, we're going to store them as the columns for our solution inputs. So we get 2, negative 3, 2 is our first solution, well, equation. Then we're going to do our RREF to find what our coefficients are. And we see that A, B, C just goes to 5, 4, 2. And since this was with respect to some arbitrary P2 polynomial, we just sub it back into the original coefficients up here. And finally, to find our final solution, we just do y equals y naught plus our kernel, always add our kernel back. And so we get 5 plus 4t plus 2t squared is just plus our kernel, which is just over here. So yeah, that's it for that. 3 is very similar to 2, except it's a bit different with the approach, especially with part B. But similarly, how we can let D and represent the order of the differential equation, we can let S represent the shift operator, and Y denote the infinite sequence. Right, so in this case, Y n plus 2, right, so we see the constant over here is 2. That just goes to S2, Yn plus 1 goes to S1, and Yn doesn't have any shift on it, it's just Y, so we can treat that as a constant. Right, so given we have this up here, we can sub it in. So Yn plus 2 goes to S2, minus 2, Yn plus 1 goes to negative 2S, and then this goes to negative 3i, with respect to the variable y, once again. And we're going to treat this with respect to our condition, which is for all n greater than or equal to 0 later on. We don't need to worry about that right now. Right, so once again, we can factor. We notice that we have negative 2 and negative 3. So you notice that negative 2 is the dominant one with respect to negative 3 pair. So you have negative 3i and then I. Yeah. Then once again, we're going to split this up into two different pieces to find our different solutions. So we get s minus 3i. Then here, since we're dealing with for all n greater than or equal to 0, we're going to go back to our condition as we defined over here. So once you split them up, you can do that. Then we're going to put our y back in after, because we're going to want to deal with that to find what yn is. So you get yn plus 1, right, because this is just first degree, minus 3yn equals 0. We're going to move this over. Then it's very similar to number 2. We're going to try to apply some operator basically to find our solution with respect to only yn, trying to cancel that out. And we see that if we want to get to y0, which is our initial condition, we're going to want to get rid of one of the y's, yn plus 1s. We're just going to get rid of one of them to get back to our initial. And that can be done just by raising the coefficient over here to the power of n. Right, so then we get yn equals 3 to the n y naught. And y naught is kind of arbitrary here. It's some scalar. So then we can say y naught is equal to 3 to the n to the a. Right, then we go over here to the general solution once again. So if we're dealing with shift operators, how we approach it is if we have as minus bi yn equals 0, we can just say that yn equals b over a to the n y naught. Once again, if it's negative b, it's going to go to positive. If it's positive, it's going to go to negative. Right, so you just got to switch the sign of the second one. The first one's going to be the same. And for y naught, since it's some arbitrary scalar constant, we can just treat it with as like c. Whatever letter you pick, it doesn't really matter, just so long as you define it correctly. But yeah, we take this general piece, as we've already shown it over here, how to approach it, so we can just do that over here. So given we have s plus I, we're just going to apply this. So we see that this is positive, so it's going to go to negative. We have no a coefficient, so just negative 1 to the n. And we have y naught, which is just going to go to b, because we do not want a and b to be the same. So therefore the solution, since this was equal to 0, is just going to be our kernel of our system, which is the same as saying 3 to the n a plus negative 1 to the n b. 3b is very similar to 2b, except we're just going to approach it differently. So if we have yn plus 2 minus 2yn plus 1 minus 3yn equals p2y, some polynomial 2. Once again, we're just going to let yn, our initial one, equal to some arbitrary p2 polynomial, because that's what we want to solve for, which is going to be a plus bn plus cn squared. So when we're dealing with y and some shift operator, what we do is we take all the n's and we just add whatever shift we apply. So in that case, for like yn plus 1, well, we're going to take our n's and we're just going to add 1 to them. We're going to store them as factors as well. That's very important to do. So yn plus 1, given we have our yn up here, that's just going to go to a plus b bracket n plus 1 plus c bracket n plus 1 squared. Same thing for yn plus 2. And then you just get this ginormous mess over here that you're going to have to expand and then group together and then simplify. Yeah, but that's just going to be a lot of clutter. Yeah, basically what you're going to do is just going to expand this, simplify it as best you can. Then similar to question 2, you're just going to group them all together according to their coefficient degrees. Here we have 3 different pieces, so we're going to get 3 different equations. Once again, we can set this up as a matrix, or REF, to find our coefficient solutions. And after doing all that, we get a is equal to 0, b is equal to negative 1, and c is equal to 1. Since from the above, this is with respect to yn, well, we look at yn and then we just store those coefficients back into the original equation. So a goes to 0, the constant's gone. C is 1, so we have n squared. And b is negative 1, so that means we're going to have negative n. So our solutions, very similar to number 2 again, it's just going to be this piece over here plus the kernel. So you get yn plus kernel of our system, which goes to n squared minus n plus, and then our kernel. The true and false ones. Okay, so the kernel of a linear transformation T from a vector space V to a vector space W is a subspace of W, while the range of T is a subspace of V. We see that this is false by definition, and we have an example from question 1, where we had T, V goes to W, kernel of the T is a subspace of V, and range of T is a subspace of W. Once again, if you want an example of this, you can just go back to question 1. So let A be an M times n matrix, then B is a vector in column space of A if and only if AX equals B has a solution. This is actually very similar once again to question 1 that we did. You can see that there. But more generally, by definition, this is true. Like the column space of A is equal to the set of B's, where is an element of Rm, such that B equals AX is an element of Rn. If T is a linear operator V, then T to the 3 minus 2T plus 3I is also a linear operator of V. This is also true once again by definition. Right, so we can say that a linear transformation in some vector space V will preserve exponents, scalar multiples, and the identity properties in V, where these are all pieces that we've used over here. So So given two distinct vector spaces V and W, if T is a linear transformation from V to W, and S is a linear transformation from W to V, then S plus T is a linear transformation from V to W. We see that this is false, right? S plus T is not a properly defined mapping, and we can quickly just write them out. We see that the order is wrong. If the order were reversed, right, if it were S goes to V to W, then S plus T would be V to W as well. And linear transformation operator would be preserved, right? There's a little proof that you can show for that. Maybe I'll do that later. So given we have these three vectors, it's like, is this linear independent vectors in R3? So there are two ways to check this. The first way you can check this is by setting these vectors, storing them as a column matrix, basically over here. Then you're going to set them equal to the null space. So after we do that, then you RREF, and you're going to look at the number of pivots you have. So in this case, we have two pivots, and we have one free variable. There is a property there's a theorem that if you have a free variable, then you can say that it is linearly dependent. So we're going to use that here. Since our matrix has a free variable, this set of vectors is linearly dependent. The second way to check that is to try to find some linear combination of vectors within the set that can create each other. So we notice that V3 can be constructed from 2 of V1 and 1 of V2. So since it can be constructed by other vectors within our set, that means that this set is a linearly dependent, yeah. So is the independent vectors in PT, is this linearly independent? Once again, we can store them as a matrix for a column space. We set that equal to the null space. We see that after RREF, we have no free variables. So we can use the theorem. Therefore, since we have no free variables, this set of P2 vectors is linearly independent. And I have a little tip down here. If the dimension of the set is greater than the dimension of the space, then the set is linearly dependent. Right? This has to be true. And there's just 5. So let T is this P2 to P2 defined by some transformation. Find the kernel of T and the range of T. Right, so the kernel of T, once again, is just the transformation set equal to 0. So since this transformation goes to this, we can set this equal to 0. We get 3 different equations because we have 3 different degrees. Constant first, second. After storing these as a matrix in RREF, we see that the solutions are just A0, A1, A2. They're all equal to 0. So since they're all equal to 0, that means that the kernel of T is just equal to the set of 0. Then for the range of T, we're just basically going to set the transformation result equal to the space that's going to, which is P2. So we have some arbitrary P2 polynomial. So the transformation is P2 to P2. I highlighted over here, which you want to look at. But after we do that, we're going to get 3 equations once again. Then we're going to RREF. In this case, we only have to look at A. We do not have to do this RREF with respect to the solution set because we can use another theorem or fact to figure out what the range is going to be. And this just makes it more complicated. You're going to have to deal with massive, basically solution equations, which is not very nice. So after RREF, just the A, we see that this is non-singular, right? It has all the pivots and all the columns, all the rows. So therefore, this is not singular, which implies that it's invertible, which implies that if it has a solution, it has a solution for any A, B, C, which implies that the range is going to be P2. And the reason why we can say this is because, well, it says that any A, B, C, which is with respect to P2, how we've defined it up here, has a solution, which means that the range of T is going to be the entirety of P2. It's going to cover all of it. That's basically it.